Okay, today we're going to be looking more about projectiles and also the role that gravity plays in the motion of orbiting bodies. So we discussed before how, let's consider something that's moving really quickly, like a bullet. It looks like the bullet goes in a straight line and isn't subject to gravity. If we were to just throw a ball at a low speed, we can see it falling. We can see that ball falling to the ground. But a bullet looks like it goes in a straight line. But the bullet feels the gravity pulling on it in the same way that every body, whether the ball or a lead weight, would feel that gravity pulling it to the ground. But because the horizontal velocity is high, the distance it goes before it eventually hits the ground is going to be long. And so it's really important to remember that anything that's travelling at high velocity experiences the gravitational pull downward, and that high velocity, although it's able to go quite a long distance, that high velocity doesn't increase the length of time that that object is in the air. And that's a really important fact, just to get your head around, that the horizontal velocity does not increase the length of time that an object is in the air. Now this brings us on to the physics of satellites. Now, if we think about the Earth, let's draw some weird countries, nothing like the Earth. So here's our Earth, massive gravity, and in space, there is going to be no air resistance, no friction or drag. So let us consider an object in such circumstances that is now let's consider an object with a high horizontal velocity, and there's no air resistance and there's no drag. So it's in space, and we fire this object in this direction of its horizontal velocity. Now this object is still going to feel the effects of the gravitational pull of the Earth. So it's still going to fall towards the Earth. But if this horizontal velocity is so high that it's going to, as it falls, it's never going to hit the Earth. It's going to be as the curvature of the Earth is going to fall away from it. So it's going to have the effect that it's going to begin. Oops, it's a dodgy orbit. Oh, the rubber didn't work. It'll have the effect that as it is drawn in towards the Earth, the gravitational pull of the Earth pulls this satellite down, this object down. It's never going to hit the Earth. It's just going to keep falling away from the surface and begin to enter it. So this is why satellites another objects, for example, the International Space Station, they appear to be just floating above the Earth. They're not floating. Satellites don't float. If they were floating, if you just had something floating there, it would just plummet down to the Earth. That doesn't happen. Satellites have high horizontal velocity. We call it orbital velocity. Now, the closer you are to the Earth's surface, the higher your orbital velocity is. So, at an altitude, let's draw, this is our Earth. And if, say, we're here, and this height is 124 miles, which is the same as 200 kilometers. And here's our satellite. It must have an orbital velocity of just over 17,000 miles per hour. So if it's less than 17,000 miles per hour, it's going to kind of move and it's going to crash into the Earth. But over 17,000 miles per hour, it will go into orbit. Now, if you have, this is going to be the Earth again, and this time, if the orbit is much higher, so at a higher velocity, the effect of gravity on the satellite is going to be slightly less. If we get 22,223 miles, that is 35,786 kilometers. The orbital velocity must be 7,000 miles per hour. Now this is quite a special place for orbiting satellites. At this height above the surface, the orbital velocity will give you a circumference of orbit. That means that at this height, the orbit takes 24 hours, which is obviously the same as the rotation of the Earth. Therefore, the satellite will remain above the same point on the Earth. Now let's draw this a bit better. Oh dear me, that's awful. That's better. So this is our Earth. There we go. Terrible, nothing like the Earth. Here's our satellite. Here is our 22,223 miles. And this is our satellite that's going to orbit the Earth in 24 hours. So this is going to always be following this point around the Earth. Now, so therefore we call this a geostationary orbit. Now these are always above the equator, and they're important for weather satellites and communications. So if you have 3 geostationary satellites, they're all above the same height. What these means, you can send, wait a minute, I'll change the colour of that to green. You can send a signal to each of these, and it won't affect, they're not going to be affected by because of the curvature of the Earth. So you can, so for satellite communications, that's how we can communicate globally, regularly, by using these geostationary satellites. And it also allows weather updates, so we can monitor the surface of the Earth with weather satellites to get information back between these two different people on the globe. Now, if you have a satellite, let's draw another one. So say we have a satellite that's a bit closer to the Earth, and there's just in Earth's atmosphere. What's going to happen here is the satellite will be in contact with air molecules, causing drag. So very slowly over time, this satellite, as it rotates, oh dear, that's terrible. It actually is going to get closer and closer and closer to Earth. On each rotation, it'll be a wee bit closer. Eventually, it will fall into Earth, or it will burn up as it gets more into the Earth's atmosphere. The friction between the orbiting satellite, which is going really fast, and the upper atmosphere will be such that it burns up and breaks up and gets destroyed. And that does happen. Not all satellites are up there forever. Conversely, here's our Earth, or my Earth's getting worse. If you have a great enough velocity, so round about 25,000 miles per hour, the velocity, the horizontal velocity is so great. What we have is, instead of spiraling inwards, we have this happen. We have the escape velocity. Now, we're going to think about gravitational field strength. So two masses, and M2, they feel each other's gravity. All matter, has a gravitational field. when two masses come into contact, these fields interact and an attractive force is felt. The greater the mass, the greater, though the stronger, the gravitational field. Now, it's believed that in the formation of stars, you get lots of dust particles, and over time, each one of these dust particles, they begin to get attracted to each other. So they would be attracted to each other there, and then they'll join together, and now they've got bigger mass, so they're going to pull this one in, and then those three are going to pull another one in, and over time you get this coalescence of mass together, and it grows, and then once these atoms are pulled closer together, it allows for nuclear fusion to occur within the gas cloud, and a star is born. Likewise, it's believed that, say you had a star, and round this star you have dust cloud rotating. These particles, these bits of rock and dust, again they're going to get attracted to each other, and they'll kind of form into planets that will then rotate around the star. So that's a very basic idea of the modelling behind planetary growth and stellar evolution. Now, large planets, i.e. greater mass, obviously will have greater gravitational fields. That's very logical. Now, on Earth, the gravitational field strength, which we've already come across, which we call small g, is 9.81 newtons per kilogram. So that means a mass of 1 kilogram experiences 9.81 newtons of force. And this force is the weight of an object. So the weight is the mass times the gravitational field strength. So that's in kilograms. G is Newton per Newton kilograms, and the weight is in newtons. So that's the force of a mass caused by the gravitational field strength of an object. So we can think about the different bodies in the solar system and the value of G, the gravitational field strength of each. So obviously the Sun is the greatest object in the solar system that has the biggest gravitational field strength of 274.13 Newton kilograms. newtons per kilogram, and then we've got Mercury, which is tiny, 3.59, Venus, she's 8.87, so close to the Earth. Then there's the Earth, which we just said 9.81, sorry. The Moon, 1.62. Mars is 3.77. Jupiter is the biggest planet in the solar system, the big gas giant, 25.95. And then Saturn, 11.08. We'll stop there. Now, the force, so when you bring the solar system, sun in the middle with all the planets orbiting around it, the motion of the planets is a product of the gravitational field interactions of all the bodies. So the sun obviously is going to have the biggest effect because it's the greatest mass, it's got the greatest gravitational field strength. Jupiter is going to be really powerful in its locality, but given that gravity acts over a large distance, that there's actually an interaction between all these different bodies within the solar system, making planetary motion a very complicated, mathematically very complicated. With the Earth and the Moon, we see the interaction of the Moon's gravitational pull on the Earth in the way the tides work, for example. Now, Isaac Newton proposed a law for universal gravitation. So he came up with a relationship between two masses. Say we've got two masses, M1 and M2, and they are some distance r apart. He was the first to people had wondered about how things are attracted and held together and before, but Newton was the first to actually put some real solid maths behind this idea, and he came up with this formula. The force, the gravitational force between two masses, is some constant g, which we'll talk about in a minute, with the mass of one multiplied by the second mass over the distance between them squared. So F is the force between masses. G is what we call the gravitational constant, and M1 and M2 is the masses, and R is the distance, and that's in meters. So force, the gravitational force between two masses, is inversely is proportional to the inverse square of the distance. Now, G is a universal constant. It's not to be confused with small g, and this is the gravitational force between two objects. Is not the same as the weight of an object on that's the force that an object exerts on, like for example the Earth, the weight that you would exert on Earth caused by the Earth's gravity. That is a different thing to the gravitational force. You could calculate the gravitational force between your mass and the mass of the Earth, and that's the attractive gravitational force between your mass and the Earth's mass. They're two different ideas. This is, although it's obviously when something's very close, the gravitational force is going to be stronger, and if they're very far away, it's going to be less. But gravity is something that is very, very strong. The gravitational constant G is equal to 6.67 times 10 to the minus 11 meters cubed kilograms minus 1 seconds minus 2. So that is the gravitational constant. But if you've got two, like say you've got the sun over here, which has got a massive mass, and you've got a planet, well, it's not a real planet, say you've got Pluto over here, it's still got a sizable mass. Even with the kind of massive distances, the sun, the gravitational pull of the sun is still going to be felt by little Pluto over here, because gravity is felt over such massive distances. Let's look at some examples. So we're going to consider the mass of the Earth. Now that is 5.97 times 10 to the 24. The mean radius of the Earth is 6.37 times 10 to the 6 meters. Now remember, this is, so when you're doing these calculations, you've got kilograms, you've got meters, and the mean distance to the moon is equal to 3.84 times 10 to the 8 meters. And we've already said G is equal to 6.67 times 10 to the minus 11 meters cubed per kilogram per second squared. So we want to calculate the force of attraction from Earth a mass 100 kilogram mass would experience if placed at the same distance from the Earth as the moon. So instead of the moon being there, we've got 100 kilogram mass. So we've got the force is G m1 times m2 over r squared. Now 6.67 times 10 to the minus 11 times, now mass 1 is going to be our 100, it doesn't really matter which one we choose for m1 or m2, times the mass of the Earth, which is 5.97 times 10 to the 24 over so the mean distance to the moon is this, 3.84 0.84 times 10 to the 8, and we square that, and that's going to be equal to 0.27 newtons. Now, things to be aware of when doing these calculations: you've got really big numbers, so you've got to be really careful with inputting it into your calculator. The main thing, just be very careful when inputting into your calculator so don't make any mistakes. So the Earth would, and this 100 kilogram object, there'd be an attractive force of 0.27 newtons. And if you were to F over m is 0.0027 meters per second squared, would be the acceleration of the mass towards Earth, and that's just from F equals ma, gives us Newton second, gives us this. Let's do another example. Calculate the force of attraction of the Earth on a 70 kilogram astronaut working on the International Space Station. The International Space Station orbits at 430 kilometers above the Earth. So notable, the distance from the astronaut to Earth is taken from the centre of the Earth. So that's something important to know. So if you think about the Earth as this big massive ball of just matter, you assume that all that matter is concentrated on one little dot at the centre of the Earth. So the radius, looking back at our previous numbers, is going to be the radius of the Earth. What we had written down on the last page was 6.37 times 10 to the 6 meters. And now we're going to add to that our 430 kilometers, but that's going to, we have to turn it into meters, so it's times 10 to the 3. So that's going to give us 6.8 times 10 to the 6 meters. So now we've got our force times G, m1 times m2 over r squared. So that is 6.67 times 10 to the minus 11 times the mass of our astronaut is 70 times the mass of the Earth is 5.97 times 10 to the 24 all over our r, which is 6.8 times 10 to the 6 squared. And that gives us 600 newtons. And this is slightly less than what an astronaut would feel if he was on the surface of the Earth. So I hope that helps.